What's up, bitches? Today we're going to learn about rotational mechanical systems and how to solve them with the state variables, okay? We're going to use this example to learn together. So, this problem is a combination of both a rotational object and a normal box, but we're going to go step by step to find their state variables, okay? So, the first step that what you want to do in any rotational or translational problem is your free body diagrams. So in this case, you have a normal box, and for your rotational objects, you're going to want to draw a disk, and you're going to draw every force that acts clockwise and counterclockwise, okay? Keep in mind that it's not like translational forces like up or down. This is like whatever's moving around, okay? So it's torques. Usually, you would have an input force saying that, oh, it's going this way, and this is your input torque, and you would just write this. That's fine. But in this specific problem, it's not a torque. It's a translational force pointing right. And we know in your dynamics class that the moment is equal to a force times the perpendicular distance to it. So in this case, it's this is your force, and the perpendicular distance is this over here, okay, this, which is equal to r. So the torque, input torque, would be equal to r f a, okay? This is just like common sense, you have to understand. Since it's pointing that way, if you pull the disk this way, it would be turning it that way. That's why I put it clockwise. Next, you have your spring over here. Actually, no, before that, sorry. Just like every object, when an object moves, its inertial force is going to act opposite to it, depending on how heavy it is. Except, normally, it would be equal to its mass times its acceleration. But for translational problems, you can't just write this. You have to consider the rotational inertia, which is j, times the angular acceleration, which is alpha. But over here, I'm going to write theta dot dot. As you could see over here, the object is turning clockwise. That's why the inertia is going to act counterclockwise. Plus, springs. Springs are going to look like rods like this, but these are, whenever you see K, that's just a spring. So the spring force is equal to the spring constant times the angular displacement. Instead of writing Kx, you're writing K theta. It's the same principle for your damper force. It's equal to B1 times angular velocity. Lastly, you have this spring over here. This is a little funky, okay? As you're pulling over here, this is basically turning that way. And the spring is connected over here. So it's getting stretched this way. So then the force would be that way. Okay? When you pull a force to an object this way, basically you would be turning it that way, which is counterclockwise. So you're going to do plus over here. Now, you can't just write K2 and theta, okay? It's not that simple over here. This is a translational force. It's pulling this way, just like FA. So, it's going to be equal to the force over here times the perpendicular distance, r. So, it's equal to r, and all that's left is the spring force, which is equal to K2. And now, since it's connected to another object, all you have to do is, to simplify your life, just pretend like this is a wall, like a stable wall. Then it would just be equal to how much this is getting pulled. Okay, it's not theta. It's equal to r theta. That's how much is getting pulled. This is the equation for the arc length distance of a circle as it's rotating. It's like with the circumference of the circle. You learn it during your Cal 3 class. This is something that you just have to like know by heart. R theta is equal to like the linear displacement of this line over here. It's equal to r theta, oh, it's K2, negative since this object is already moving to the left, it's not going to be super stretched because this is already moving to the left. So minus x. It's that easy. Now, for our second free body diagram, we know that it's moving to the left, so its inertia is going to affect to the right. There's also a spring, K3, K3x. There's also a damper force, x dot. And you also have your spring. That's like springs, almost 90% of the time, it's going to pull shit towards itself. Okay? Like that way. Understand? Over here, you don't need to write RK2, okay? Because this is like, okay, look, Newton's law says that, oh, the force is the same. Yeah, it's just when it's acting on different objects, it's like opposite direction. It's the same principle as if you're pushing on a box, you are exerting force to the right, but the box is exerting force to you to the left. It's the same force, just opposite direction. But this isn't exactly the same force, only because over here we're looking at like the rotation of the object. While over here, for this object, we're just looking at the translational XYZ coordinates of the forces. So you don't need to look at the moment equals FD. You don't need to look at this, okay? You don't need this moment shit. You just need this F. So just ignore the D. Ignore the R for in this case. Otherwise, it's exactly the same thing. We just don't give two shits about the rotation. There you go. Whoops. Okay. Now that we have the free body diagrams, the next step is to write out the equations. So just like all of your other problems, whatever is acting on the right side, you equalize it to whatever is acting on the left side. And it's the same principle for your rotational objects. Whatever is acting clockwise, you equalize it to whatever is acting counterclockwise. However, since I'm writing with a mouse, I'm just going to type it out for you guys. Hold on. Give me a second. Okay, I typed it out for you guys. It's over here. This part over here is over here. And the counterclockwise, this is over here. I just forgot to write RFA for the moment. Whoops, hold on. Let me just clear it up. RFA. I just forgot to write RFA earlier, but it's because of the moment. Same thing with here. The M, this shit over here, it's over here. Whatever's acting on the left side is over here. Okay? So, once you have these equations, you don't need your free body diagrams anymore. So, that's just it. But, like, your free body diagrams have to be correct. Otherwise, everything else is going to be incorrect in your solutions. You might get partial credits, but still. There you go. Alright, let me bring this up. Whoops. Alright. Now we can begin writing our state variables, okay? So, while I was taking this class, literally every single state variable was just the displacement and velocity. Since here we have two objects, x and v is for the mass, and for the disk, instead of writing x and v, you have to consider their angular displacement and their angular velocity, omega. Okay? Now, unless if an input is if a displacement is the input, they would write x of a as their input. You can't consider that as a state variables. But for every single problem, the state variables is the displacement and the velocity, okay? Once you consider these as your state variables, the last step is to define their derivatives, okay? You have to define x dot, v dot, theta dot, and omega dot. x dot, the derivative of x is just the velocity. Same thing with the theta, it's just equal to the angular velocity. To find these two over here, you just have to use this equation and solve for them. It's that easy. Okay? So let's start with the omega, okay? J theta dot dot is just the acceleration. It's just this. That's what we're looking for. J omega dot plus K 1 theta plus B 1 theta plus R K2 R theta negative X. Hold on. Equals RFA. Now you just solve for omega dot. So you send all this shit other side, and then you divide by J. Okay? Your final answer would be for omega dot equals 1 over J. And it also helps for you to factorize all of your variables. Okay, so theta, x, factorize all of these because they're important. RFA is just a constant. Negative. I'm just gonna. Oh, actually, hold on. My bad, guys. Instead of writing theta dot, another rule is whenever you're defining a state variable, you can't have like other derivatives in your equation. Okay, it's not like a normal differential equation. You can't have other derivatives. Since we already defined like omega. Instead of writing theta dot, you write omega. Okay, and then you carry on. I'm just gonna factorize this in my mind because I'm just built diff. Okay, this you distribute it. R squared K squared plus K1 plus R K2X. Right? Am I forgetting something? No. That's it. So we have our omega dot. Lastly, there's our velocity left, okay? The velocity dot, is over here. It's this x dot. X dot dot equals to velocity dot. So let's write it out. mv dot plus b, what was it, b2? Yeah, b2v plus k3x equals to k2 r theta negative x. Okay? Yeah, that's it. You send all this shit to the other side, and then you divide by m. So you would get v dot equals 1 over m. I'm just gonna factorize everything in my mind. You would get, hold on, negative x k3 plus k2r. Wait. No, sorry, not r. It's just k2. Negative b2v plus k2r theta. It's just basic algebra. It's nothing rocket science. You just have to follow this, and that's it. This is our last answer. And that's how you solve rotational problems. Thank you for watching. Leave a like, subscribe. Bitch.